Okay, so now I'll start going over the level 3 and 4 questions. So first of all, level 3. So let f of x be equal to cx times x minus 1, where c is a positive real number. And we let f to the power of n of x denote the polynomial that we get when we compose f with itself n times. And so for every positive integer n, all the roots of f to the power of n of x are real. And so we want to find the minimal c. And so first to do this, what we first can do is we want to show that the roots of f to the power of n of x are all in the range negative c over 4 and 1 plus c over 4. And so the way we do this is let r be a root of f to the power of n of x. And so now if we let r be equal to negative c over 4, then we have that the inverse of f of r is just this. And so then what this tells us is that we have that negative c over 4 is less than 1/2 is less than 1 plus c over 4. And this is because c is positive. And so now if r is not equal to negative c over 4, then what we get is by the quadratic formula, there are two complex roots. There are two complex roots, or two roots, r1, two roots r1, r2, such that r1 plus r2 is equal to 1, and f of r1 is equal to f of r2 is equal to r. And so what this means is that all roots of f to the power of n of x are in pairs, and the sum of each of these pairs is adding up to 1. So now we can see that there is, so if r is less than negative c over 4, then we can see that f to the power of n plus 1 of x has an imaginary root. And the imaginary root would be the inverse of f of r. And this would be imaginary if this is true. And so what that means is that all roots are greater than or equal to negative c over 4. And similarly, we already know that all the roots are in pairs that add up to 1. And so that means that r also cannot be greater than 1 plus c over 4, because if that's true, then we have that the pair that adds up to 1 with r would be 1 minus 1 plus c over 4, would be less than, so that root r prime will be less than 1 minus this, and this is negative c over 4. And we have already shown that this does not work. And so that just shows that our bound of the roots is true. And so now what we can do is let g of x equal to 1 plus square root of 1 plus 4x over c divided by 2. And so you have that g to the power of n of x is, so have that g to the power of n of x is the largest element of f to the negative n of x. And so that means that g to the power of n of 0 is at most 1 plus c over 4 for all n. And so we can let x0 be the non-zero real number such that g of x0 is equal to x0. And so we can substitute the value back into what we had, into what we were given. And so what that would mean is that cx0 times x0 minus 1 is equal to x0. And we already had that x0 is non-zero, so we can divide this out. And so x0 is equal to 1 over c. Sorry, 1 plus 1 over c. And so now, after this, what we have is that x0 is g of x is between x0 and x. And so this is true if x is greater than x0, and otherwise if x is less than x0, then what we have is that x is less than g of x is less than x0. And so now using this, we can see that g of n to the power of x approaches x0. And so we have that x0 is equal to 1 plus 1 over c, and is less than or equal to 1 plus c over 4. And so if we solve this, we can see quickly that c squared is at least 4, so c is at least 2. And so now what's left is to see if c equals 2 actually is possible. And so what we need is to show is that all of the roots of f to the negative n of x are real if g of 0, as long as g of 0 is less than or equal to 1 plus c over 4. And substituting the value of c in here, this is equal to 3 halves. And so we know that clearly 0 is less than 3 halves, so g of 0 is less than 3 halves, because g of 0 is simply just 0. And so now, next we have that g squared of 0 is less than 3 halves as well. And if we continue this onwards, we have that g to the n of 0 is less than g to the n of plus 1 of 0. And this is still less than 3 halves for all n. And so that shows that all the roots are real. And so the answer is indeed c equals 2. And so now I'll move on to the level 4 question. So for the level 4 question, you're given a sequence of real numbers, and a move is choosing 2 terms and replacing each other with their arithmetic mean. And so we want to show that there exists a sequence of 2015 distinct reals such that after one initial move is applied to the sequence, no matter what the move is, we can always continue so that the end result is a constant sequence. And so to make it a lot easier, we can let this sequence of 2015 distinct real numbers simply be negative 1007, negative 1006, so on 0, 1, 2, so on until 1007. And so this set is a total of 2015 elements. And so we can see that changing a and b to a plus b over 2 and a plus b over 2, this does not affect the sum in any way because the sum here is a plus b, and this sum is also a plus b. And so since the sum is always constant, that means that the initial sum is, we know that the initial sum is 0. Initial sum 0. And so the average is also 0. And this remains constant throughout the entire process because the number of elements remains constant as well as the sum of all of the numbers. And so we can see that there are a total of 1007 pairs of A and negative A. And so after two of the numbers are picked, after the first pair of numbers is picked, there are at least 1005 pairs. I should say pairs. Okay, 1005 pairs of x negative x, such that they're still add up to 0. And so first of all, we can just get rid of all of these pairs by applying the operation to each x and negative x. And so that gives a total of 2010 zeros. And so there's a total of 5 elements left after this operation is over. And so we can let these 5 elements be A1, A2, A3, A4, and A5. And in order to be able to apply the operation as many times as necessary, we want the total set of that we are applying the operation on to be some power of 2. And so we can add additional 3 zeros. And so we can just let these be A6, A7, and A8. And so first we apply the operation to, so initially it is, the thing is, the 8 numbers are A1, A2, A3, A4, A5, A6, A7, and A8. And so now, after this, we can let M1, we can let this A1 and A2 reach M1, where M1 is just A1 plus A2 divided by 2. And so this would be M2 and M2, and this would be M3 and M3, and this would be M4 and M4. And so it would look like this. And so after this, we can let the operation applied to M1 and M2 be equal to M11. So operation on M1, M2 equals M11, and operation on M3, M4 equals M12. And so M11, 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 M12, 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 M12. And so the way this works is you can pair these up in the way that they're drawn. And so after this, we can let M11 and M12, the operation applied to these, be M111. And so that means that all of these are just M111. M111, 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 and M111. And so this process just sends these together and they pair off. And they pair off into these 8 numbers. Okay. And so the initial sum here, so the initial sum is, the sum is equal to 0 because we initially had that the sum of the entire sequence was 0, and all the terms we canceled out prior to these 5 also had a sum of 0, which means that these 5 elements must also have a sum of 0. And at the same time, these were all zeros in the first place. So the total sum here is 0. So the total sum here is also 0. And so we have that M111 is also equal to 0. And so that means that all of the terms are now equal to 0. And so the problem initially just wanted us to show that after a finite sequence of moves, the end result would be a constant sequence no matter what the initial move was. And so we've shown here that no matter how we start off, the end result is a constant sequence of 0. And so, yeah.